Welcome to The Explainer. Today, we're demystifying something you probably interact with every single day, but maybe haven't really thought about in terms of its physical real estate. Exactly where does artificial intelligence actually live and operate?
So let's dive right into this. When you ask your smartphone a quick question, or say your smart security camera instantly identifies a face at your front door, where's that intelligence actually happening? Is the brain sitting right there in the palm of your hand? Or is all that heavy-duty processing happening in some massive, humming server farm thousands of miles away? To figure that out, here's our roadmap for this explainer. We're going to cover the AI location debate, make the case for edge AI, look at TinyML in the real world, benchmark some actual edge performance, and then cap it off with the ultimate hardware showdown. We'll start broad and then zoom all the way in on some rigorous hardware testing.
All right, kicking things off with Section 1, the AI location debate. This whole conversation really boils down to the classic tug of war between centralized and decentralized tech.
We essentially have two heavyweight contenders here. On one side, there's cloud AI. This processes your data on remote servers, giving you access to basically unlimited, totally scalable computing power. But the catch? High latency, because it's completely at the mercy of your network connection. On the flip side, we've got edge AI. This processes data directly on your local devices. Yes, you are limited by the physical specs of whatever gadget you're actually holding, but you get incredibly fast, low-latency processing. Plus, it works completely offline.
Which brings us right to Section 2, the case for edge AI. Let's look at why computing at the edge is picking up so much incredible momentum right now.
Just look at the sheer scale of this number. $20.78 billion. That is the massive projected size of the edge AI market. And what's genuinely staggering here is that it's expected to grow by roughly 22% every single year between 2025 and 2030. Financial momentum like that tells us one thing for sure. Businesses are heavily invested in bringing processing power way closer to the source.
So the crucial point is understanding exactly why this massive shift is happening. Edge AI brings some huge benefits to the table. We're talking reduced latency for real-time processing and seriously enhanced data privacy because your sensitive info literally never has to leave your device. Plus, you get that offline functionality and you lower your bandwidth costs. Now, obviously, there is a trade-off. You are strictly limited by the physical computing juice of the device itself. But honestly, for a lot of real-world applications, the privacy and speed perks heavily outweigh having a bit less compute power.
So, how are people actually using this? Let's get into Section 3, TinyML in the real world, and see how we bridge these theoretical concepts into reality.
Enter TinyML. Now, TinyML is a highly specialized subset of machine learning, and its entire focus is on deploying lightweight models onto resource-constrained devices. We're talking tiny microcontrollers, your smartwatch, or basic embedded systems. It is basically the secret sauce that makes advanced AI capable of running on tiny, super low-power hardware.
And we're already seeing TinyML transform completely different sectors. In healthcare, it's powering real-time patient monitoring right at the bedside using IoT devices. In retail, you've got smart shopping carts managing inventory locally without even needing a cloud connection. For security, we're looking at computer vision and object detection running directly on local cameras to give you instant notifications. And out in the industrial sector, they're using it for gesture recognition to run human-machine interfaces right there on the factory floor.
Okay, let's take these concepts into the lab. Section 4, benchmarking edge performance. It's time to see how this hardware actually holds up under pressure.
And this brilliantly illustrates how we measure that. Researchers from George Mason University used a framework called PICO, which stands for Performance of Inference, CPU, and Operations. It's this really cool modular platform-agnostic pipeline that they designed specifically to systematically stress test these embedded systems in true real-time scenarios.
The benchmarking methodology here is rigorous, following 4 very strict steps. First up, dataset preprocessing to prep the inputs. Second is the actual inference execution. Third, they do metric collection, which means meticulously logging the latency, the CPU usage, and the memory. And finally, visualization and analysis. And just to make sure their data was totally rock solid, the researchers ran these models across 100 complete iterations.
Which brings us to the main event. Section 5, the ultimate edge showdown. We've got a direct head-to-head battle between two super popular hardware platforms running the exact same TinyML models. Let's see what happens when they actually put this to the test.
Let's meet our contenders, shall we? On the left, we have the BeagleBone AI64. This board is explicitly built and optimized for AI. It's packing a Cortex A72 processor clocked at 2.0 GHz with a massive 8 gigs of RAM. And on the right, we have the beloved general-purpose Raspberry Pi 4. It's running a slightly slower Cortex A72 at 1.5 GHz with only up to 4 gigs of RAM. So on paper, the BeagleBone has a huge resource advantage, while the Pi is really just known for being a cost-effective all-rounder.
But wow, look at these results. There is a massive latency gap here. For gesture classification, the BeagleBone took 9.49 milliseconds. The Raspberry Pi 4, it knocked it out in a blazing 1.76 milliseconds. And it gets crazier. For the really heavy MobileNet V2 image model, the BeagleBone took over 2100 milliseconds, but the Pi cranked through it in just 513. Against all the odds, the general-purpose Pi absolutely crushed it, showing a massive latency advantage across all three models.
And that leads to a pretty definitive finding. The Raspberry Pi 4 achieved lower latency across the board. It basically proves that if you're building an edge device and you absolutely need real-time, immediate responsiveness, the Pi 4 was the clear, undeniable winner here.
Now, what's really interesting about this slide is the wild contrast in CPU usage when they ran that heavy MobileNet V2 model. If you look at the BeagleBone, its CPU usage is just spiking sporadically, averaging out at over 51%. But over on the Raspberry Pi's graph, things look totally different. Its CPU usage is way lower, much more controlled, averaging just under 29%. So not only is the Pi doing the inference way faster, it's doing it while barely breaking a sweat.
So let's quickly summarize the final resource trade-offs from this academic benchmark. The Raspberry Pi 4 ended up using about 23% less CPU than the BeagleBone and roughly 6% less memory overall. Now, I should definitely note that both platforms were equally accurate. They both delivered highly stable, identical prediction confidence, hitting 0.98 for the gesture classification. But the final verdict, it's pretty clear-cut. The Raspberry Pi 4 is far superior if you're deploying in a battery-constrained, low-latency edge environment.
All of this leaves us with a pretty fascinating, provocative thought to close out our explainer today. If a cheap, accessible, general-purpose board like the Raspberry Pi can run AI locally with such incredible low latency and resource efficiency, what exactly does that mean for the massive, power-hungry cloud data centers of tomorrow? Honestly, it seems incredibly likely that a hybrid future, where hyper-efficient edge devices work perfectly in tandem with the cloud, is going to completely reshape our technological infrastructure. Thanks so much for joining this explainer, and remember, never stop questioning how your technology actually works.